And to really start gravity, we've got to start with the ancient Greeks. All right, ancient Greeks. We've actually already talked about this concept. Who from ancient Greece provided an explanation for why things come towards the surface of Earth? So Newton, the apple guy, was not a Greek, and that was definitely a couple thousand years after this. Some philosopher, Aristotle. All right. So Aristotle was the first to provide an explanation for why things came towards the surface of Earth. And Aristotle didn't describe it as gravity. Aristotle described it as a property of objects. He said it was the innate property of objects to come to rest on the surface of Earth. It is the innate property of objects to come to rest on the surface of Earth. So he's describing not that Earth is pulling them down, but this is part of what objects' definition is. It's part of their existence, is that they rest on Earth. That's what they do. In addition, Aristotle also had a separate set of laws for the heavens. The ancient Greeks viewed the universe as being created out of concentric spheres. At the very center of those spheres was Earth, and that was the domain of humans. And since humans suck, the Earth is imperfect. But since the gods are perfect, every sphere outside of that was also perfect. So the construction of the universe around a geocentric model basically went with there was a set of rules for Earth and there was a set of rules for the heavens. A set of rules or laws existed for Earth and a separate set for the heavens. And that understanding was part of what built into the ancient Greeks' construction of the universe itself. So we know that they put the Earth at the center, and then following the Earth, we had the moon. Beyond the moon, we had Mercury, then the sun, Venus. I'm running out of space. Mars, Jupiter, Saturn. And that was the extent of the ancient Greek universe. And each one of these planets existed in its own perfect crystalline sphere. So each planet exists in its own perfect crystalline, crystal-like. Well, they thought that there existed like actual spheres, kind of like glass that you could see through, in a way, but transparent. Actually, these stars were the final sphere on the outer edge. So, with stars shining through them. All right. Why were the ancient Greeks, if this was kind of just based on almost a religious understanding, why were the ancient Greeks considered to be some of the fathers of modern science? What about this would imply science at all? All right, I got like 5 answers. Awesome. I'm going to start over here and move over. So, yeah, Aaron. Okay, so because they had planets in motion, All right, moving over. Who else had something they chimed in with? Matt, did I see you had something you added? Okay, Riley. Okay, they knew there was more stuff out there to explore. Astrid, did you have something you added too? Okay, so they just explored the natural world as a whole. Others who chimed in with something? Say again. Okay, they tried to make hypotheses. All right. In addition to a lot of what you guys are saying, not necessarily all of it, but a lot of what you're saying, um, they were making actual scientific hypotheses, and more importantly, they were able to actually look at their information. And when they saw or made observations that conflicted with their hypotheses or their theories, they recognized that they were wrong and they had to change their thinking. So one of the things that they could observe is what we call the retrograde motion of Mars. So this is a whole bunch of pictures taken over the course of many, many nights from October to May. And you'll notice that Mars comes this way each night. Then it slows down, stops, and starts going backwards. This is what we call retrograde motion, yes. If Mars is observed to do this, that means Mars can't just orbit us. Something else has to be going on here. So again, backing that up. So Mars comes through, and if it was just orbiting us, that'd be fine. But then it slows down, stops, goes back the other way. And this motion is what we call retrograde motion. Retrograde simply meaning moving backwards. And if Mars does that, it can't be on a circular orbit around us. So the Greeks modified their understanding of the universe. So retrograde motion is the apparent backwards motion of planets in their orbits. Apparent backwards motion of planets in their orbits. So Aristotle and his contemporaries devised this set of what we call epicycles. So not only did they believe that the planets were orbiting us, but they believed that the planets were orbiting on small circles on those large orbits. So if we took Mars, for example, it had a circle that it was going around out here, and then it was going around on its large orbit as well. So it was really forming a path like that. However, because the ancient Greeks could actually do math, when they calculate out, well, how often should Mars go in retrograde then, they found that it was far too often. So they put another circle on here, and another circle, and another circle, and another circle, and another circle, and they had compounding tiers of circles of orbits on top of each other. So a planet wasn't just going around Earth, it was going on circles, on circles, on circles, so that they could mathematically add up the motion of all these circles to get what they observed in the sky. So epicycles are concentric orbits of planets calculated in order to try to explain retrograde motion. Retrograde motion. All right. Questions about retrograde motion, epicycles, or the geocentric model of the universe? Yeah. So the retrograde itself is when we would, from Earth, see the sun move, or sorry, see Mars move backwards in its motion. Normally it would be going like this, and then occasionally we see it move backwards. So one of these little loops would be retrograde, okay, as it would move backwards in its apparent orbit, and then back into its forward motion. Mars does not move backwards this often, which is why they had to make all these compounding circles in order to get rid of a good number of these loops. Good? Yes. So that video I showed, those are actual pictures that actually can be observed. Okay. Other questions? So this is the understanding of the universe that we worked with as a human race for 2,000 years. That's kind of what we just stuck with, because who was in charge of education for that 2,000-year gap from the ancient Greeks until the late 1400s? The Catholic Church. And the Catholic Church saw Aristotle's teachings and thought, hey, these are pretty good. We're going to adopt these. These are now church doctrine. So that wouldn't normally be a problem, except that trying to improve church doctrine, well, that's not really a thing. You don't get to improve on perfection. You get burned at the stake for trying to. So for 2,000 years, because Aristotle's teachings were adopted by the church, we really didn't make any progress. So then we get to the late 1400s. And thinking back to your Western civilization, who do we get? Question though, go ahead. Oh, okay. Pre-Galileo. I heard it. Copernicus. So I'm just going to write in a few notes here that aren't specific to Copernicus, but just kind of that stuff we just mentioned. Aristotle's teachings are adopted by the church. Church doctrine and the Inquisition and all of its terrifying glory exists. All right. So Copernicus actually worked for the church. If I remember correctly, on his list of many jobs, he happened to be a bookkeeper for them. Like he did some of their accounting. In addition, he was also a doctor of sorts. He was kind of a man of many talents. And since he also worked with the church, arguing with the church's stance or Aristotle's stance, really it's the same thing, was kind of a no-no. So Copernicus was able to avoid the Inquisition when he published his book on the orbits of the planets. Anybody happen to know how he avoided the Inquisition? Kind of a cool trick. Yeah, he published it on his deathbed. So literally the day he died was the day the book published. And you can't be burned at the stake if you're already dead. I mean, it doesn't hurt. So published his model of the solar system, or I should say of the universe at this point, from his deathbed. Peace out. All right. So published from his model from his deathbed can't be tried by the Inquisition. And Copernicus' model is much more similar to what we've seen before, where we have the sun at the center, then Mercury, then Venus, Earth, with, of course, the moon, followed by Mars, Jupiter, and Saturn. So, question for you. Why didn't Copernicus's model of the universe take off? Why wasn't that kind of the done deal? He's published it, it's noted or known well. Why was, other than the power of the church, any good reason? Okay, no one wants to back him up. What'd you say? These are still circular orbits. And when you do the math on it and make the observations, that still doesn't actually fully account for Mars's motion. And we still need epicycles on this system in order to observe what we actually see with the stars. So he took the sun, put it at the center, and still mathematically needs this massive set of epicycles to try to explain the motion. So it's no neater. It just now has some added heresy. So, first of all, he wasn't able to stick around to defend his arguments. Able to defend his arguments. And he still needed epicycles. Okay. So mathematically, his theory is not that much better than Aristotle's. It really doesn't do anything for us. Okay. Who followed Copernicus? Pre-Galileo. Not as pre. There was one who starts with a K. Yep. Kepler. But we're actually going to talk about the most interesting man in history, Kepler's mentor. So this is an individual by the name of Tycho Brahe. So I've got a whole bunch of interesting stories on Tycho. So a couple of goals here. First of all, my first goal is obviously to give you the information about what did Tycho Brahe do for astronomy. My second goal here is to convince you that Tycho Brahe is in fact the most interesting man in history. So, start out, he lives in Denmark. And not only does he live in Denmark, but he's a nobleman in Denmark. However, he wasn't really born into that role. He was kidnapped into that role. His parents, I don't quite understand how Dutch nobility worked in the early 1500s, but for some reason his parents weren't nobles, and his noble uncle kidnapped him and raised him as his own. So he became a noble, because I guess when you're kidnapped by one, that's what happens. So kidnapped by rich uncle. All right. So if you're a nobleman in the 1500s, I'm just going to write 1500s here. You obviously don't really have to work for a living. So what do you probably do a lot of? Tycho Brahe was a lush, to kind of make an understatement. And Tycho Brahe allegedly first became interested in astronomy when stumbling home after an evening and witnessed an object light up in the sky that was as bright as the moon. So initially, we kind of look at this and we also look at Brahe's track record and say, yeah, you were probably just inebriated. However, he actually recorded very precisely where he saw it, what was around it, and there were other recorded sightings, yeah, thank you, of this same object. And with Brahe's information, we can actually look at the spot in the sky where he claims this thing existed. And if we look through it with telescopes, we actually find a supernova remnant that should have exploded in the early 1500s. So we actually have some validation for this mildly drunken claim that he made about witnessing a supernova. So witnessed a supernova while walking, big air quotes there, home. He recorded the information about where he saw it, and this is what really kicked him off into interest in astronomy. Now, if you're going to be a scientist in the 1500s, that's not a paying job. You need a real source of income. Tycho really doesn't need a real source of income. He just kind of has money because he's a rich nobleman. And so he dumps all sorts of money into creating, I don't want to say telescopes, because they didn't use optical lenses. They were really just large iron sight protractors. And he created them in a gazebo on his island, and he kind of just had his own building for these things. So invested in making the largest and most precise astronomical measuring tools that did not use lenses. Worth noting, we've got at least another 70 years before the telescope's even invented here. And he was actually precise enough with his measurements that he was good down to 1/60th of a degree. He could plot positions of stars, positions of planets using these devices. Precise to 1/60th of a degree. Now, it is believed that actually only Tycho could be that precise with this set of instruments because he had a significant advantage on anybody else who would work with him. And that's that he could actually get closer to the devices than anyone else. Because during an argument with, I believe it's his cousin, and it's debated over whether or not this was an argument over a woman or if it was an argument over astronomy. Well, if you're in the 1500s and you're having an argument and you can't come to a resolution, what is the only way to solve that argument? Sword fight, duel. And during that duel, he lost his nose. So, lost his nose in a duel. Cousin. So this gave us two things. First of all, we think he was able to get closer to the machine that he actually built because he didn't have a nose in the way, so he could get more level. Yeah, it's gone. And for the rest of his life, he carried around with him a box of glue. And what we found out was, I believe it's a bronze nose that he would dip in the glue and then adhere to his face. And when he actually went about doing his measurements and such, he'd remove the nose from his face and work on the machine. So, carried. He adhered to his face. I mean, he's rich enough. Buy another one. Right? Allowed him to get closer to measuring devices. All right, so Tycho not only took great pride in collecting data and having the best astronomical data that had existed to this point, but he also was really big into sharing that information. So he wanted to have the king's ear. I mean, being a nobleman, that was a little bit easier, but he wanted to let the king know what was he discovering, what was he finding, what was he learning about the stars. And the best way to get this information out is, of course, to have a party. And he was very frequently had these parties where there was an incredible amount of drinking because he's Tycho Brahe. But also he was able to show them the information he was using. He was able to get more investments in his measuring devices and proceed with his research. So through parties to promote astronomy. To give you a little bit of perspective as to how crazy Tycho Brahe's parties would get, there's documentation that his pet elk was so drunk it fell down the stairs and died. A, he had a pet elk. B, the pet elk got drunk. And C, it fell down the stairs and died. And yes, I'm writing that down. All right. So, promotes astronomy, has some of the best measurements, tries to invest a whole lot in it. Andy. I frequently throw in a bonus question section where you can capitalize on that. So, I have two examples. Neither example is proven otherwise. Yeah, probably. All right. So, next up, amongst his works, Tycho also generated his own system for the universe. He had his own ideas to how it was constructed. And because he liked not being on fire, he put the Earth at the center, which of course is then followed by the moon, which is then followed by the sun. And here's where he diverges with the Catholic Church. He definitely says, oh, the Earth doesn't move. That stays stationary. The sun definitely goes around us. But Mercury goes around the sun. And Venus goes around the sun. And Mars goes around the sun. Etc. So rather than say that all the planets orbit the sun, he avoids the claims of heresy by saying that Earth doesn't move, Earth is stationary. Everything else goes around the sun, and the sun goes around us. So we're still the center of the universe. Mathematically, this is just changing your frame of reference. It's the same thing as Copernicus' system. He's just trying to avoid any issues with the Catholic Church. So mathematically, the same as Copernicus' system. Now, where Tycho Brahe really gets his claim to fame is not the work that he, but what his assistant was able to do with his information. Really into making the measurements, he wasn't really into the math, and for that job, he had Johann Kepler. Okay. First of all, Kepler was basically a paid assistant of Brahe's. He recorded all the data, really did all the mathematical work. And did mathematical work. So Kepler had a huge advantage over any other astronomer at that point in that he had the best data to work with. He had an advantage that nobody else could work with. Unfortunately, it wasn't until after Brahe died that he actually started to make his break. So putting the last capstone on Brahe here, he died, but there's only one way to go out if you're Tycho Brahe, and that's with a bang. So at one of his parties, sitting down, eating, Brahe believed it was impolite to excuse himself to go relieve himself. So instead, he sat there and just dealt with it. Then, and kept drinking and kept drinking until his bladder ruptured. And he's dying due to infection caused by a bladder rupture. Died from ruptured bladder. Okay. So moving on with Johann Kepler now. Kepler's with Brahe's data. He's got all of that information. He's got more mathematical genius than Brahe had, and he develops an incredible set of epicycles. A system much like Copernicus's, but mathematically more fine-tuned. And he makes a huge prediction with his system, and he tries to predict where one of the planets, I can't remember which one, I think it was Mars, is going to be at a certain date several months out. So he predicts based on his new system that he's literally taken years to develop. So created system of cycles over the course of years. And when it comes to actually the position of this planet in the sky, he is by 8 minutes of arc. So prediction was off by 8 minutes of the minute of arc is of course 1/6 degree. So 8 minutes of arc, that's about half the width of the moon. So, maybe about that far from where he thought it should be. I mean, you and I would look at that and say, wow, yeah, we're pretty good at this. This is really good. That was right where we expected to be after several months of waiting for the planet to get in position. However, Kepler, what's the only law Kepler can do here? One step short of that. Throw everything out and start from scratch. Because 8 minutes of arc is 8 times than the precision Brahe was claiming. And Kepler believed in Brahe's data that much that he threw out years worth of work and completely abandoned the system that he had created. Which is good because this is also when he finally abandons epicycles. These circles on circles that people have been using literally thousands of years to explain retrograde motion. Kepler's going to get rid of them. It's a new system that revolves around 3 laws. Laws. Law 1. Orbits are ellipses with the sun at one foci. Orbits are ellipses with the sun at one foci. What that part of an ellipse is in a moment. The other part of this was that the average distance from the sun to was the length of the ellipse's semi-major axis. The average, still part of the same, distance from sun to planet is the length of the ellipse semi-major axis. All right. So to actually draw this, I'm going to take this. I'm going to tape down both ends of this. Let's go about there. Let me make sure this is here. Try it in this direction as well. So drawing an ellipse, what I'm doing is simply making sure that the sum of the distance from one foci to the edge plus the distance and the distance to the other foci from the edge is constant. So not a circle, actually an ellipse. We can prove that by measuring across here, showing that this distance is 115 meters, and this distance is about 102 millimeters. So pretty circular, but actually an ellipse. Being flattened, this is wider. These 2 points where I've got the string tied down are what we're going to call foci. Okay? One of those has the sun. Okay? If we have a line from one edge through both foci to the other edge, we have what we call the major axis. Anybody feel like they're in a geometry class? Never. Major axis. If we draw a dividing it in half the other way, we have the minor axis. Okay. You'll notice from this first law, the length of the semi-major axis is the average from the sun to our planet. The semi-major axis is simply half of the major axis. Is major axis over 2. Okay, questions about Kepler's law? Okay, second law. Kepler's second law indicates that sweep out equal areas in equal time. Planets sweep out equal area in equal time. This is really just a different version of conservation of angular momentum. Conservation of angular momentum wouldn't be developed for another 100 years, so he had no idea what that was, but he was making observations that are actually the same as. So, explain by conservation of angular momentum. So what Kepler was noticing, that if, again, this one, the sun, if you draw radii to the sun, and let's call this point A1, and this here, point A2, this sweeps out an area that you could mark as based on pizza slice. So, area. If you found two other locations, and I'm just going to pick a pair of locations out here, B1 and B2, and we found the area of this pizza slice. If these two areas are the same, then that means the time it takes to go from here to here and from here to here must also be the same. Okay? What he's showing is that when the planet is nearby the sun, it's going to have to move faster. And when it's further from the sun, it's got to slow down. Okay. Questions on that idea? This one here? The focus number 2, I actually almost always get asked this question. There's absolutely nothing in that spot. We've looked. There's nothing there. Is for a planet? Yeah, is ellipses. Yep. Yeah. This area and this area are equal. Because areas are equal, that means the amount of time it takes to go from here to here for a planet is the same as the amount of time it takes to go from here to here for a planet. So it must travel faster here and slower here. If the area is equal, or if your time between these points, then your area will always be equal. Did that answer your question? If it takes the same amount of time here as it does from here to here, then the areas have to be equal. All right. Last one, third law, is really just an equation, t squared over r cubed is equal to t squared over r cubed. And what we mean is third and final law here, for any orbiting the sun, its period squared divided by its semi-major axis cubed is a constant ratio for any object in the solar system. And we will work more with that one tomorrow. Because or do I have 5 minutes? Oh, I have 5 minutes. I'm thinking next hour. So I'm going to make sure I write down an explanation. T is period or year, and R is semi-major axis. So we can do an example here if we look at, say, Earth and Jupiter. Okay? Earth as planet 1 and Jupiter as planet 2. I happen to know that Jupiter is, I believe it's 11.8 times as far as Earth. And we can figure out how long it takes Jupiter to go around the sun simply based on that piece of information. Okay? So I want to check that since I've got time, actually. Let's see here. I'm sorry. I'm thinking that's the year. 11.8 times Earth's year. So it takes 11.8 years for Jupiter to go around the sun. Okay? From that, we can figure out how far it is from the sun. So how long does it take Earth to go around the sun? 1 year, 1 squared. How far is Earth from the sun? So we could look that up, or we could do what Kepler did, which is say Earth is 1 Earth-Sun distance from the sun. And we actually describe that as an astronomical unit. 1 astronomical unit is the average distance from the Earth to sun. So we're just going to do this in astronomical units, 1 cubed. Okay? Equals, he knows that it takes Jupiter 11.8 years to go around the sun. So how far is Jupiter from the sun? Well, all he's got to do is now solve this. 11.8 squared. And then I'm going to multiply r cubed up to the other side, take the cubed root. Cube root of that, I get roughly 5.2. R equals 5.2 astronomical units, or 5.2 times further from the sun. This is Mr. Carney. Yep, we'll do. But, all right. So, this is a system that we find works not just for the solar system, but for literally any system of orbiting objects. We could work with, sure, we could talk about Earth and Pluto. We could talk about Venus and Mars. We could talk about Mercury and Saturn. Or we could talk about the Moon and the International Space Station. We could talk about the Hubble telescope and a satellite for phones. Any objects orbiting the same central object work with this relationship. So works for any system of orbiting objects.